In this video, we discuss the derivation of the rotating atmospheric equation. In the previous video, we discussed the non-rotating atmospheric equation, which is in this form, including the pressure gradient, gravitational force, and frictional force. And we denote the non-rotating frame, otherwise known as inertial reference frame, with parentheses and a subscript A. And what inertial means is if we're standing at a point in space and we're not moving, but the Earth is rotating away from us, things will move in a straight path and according to this equation. However, if we were on the Earth itself and rotating with it, which most of our data collection is, for example, satellites rotate with the Earth to some degree, and so from that non-inertial reference frame that we are at on Earth, there are these apparent forces that will show up that will make it look like things are moving curved off their trajectory, but in reality they're actually moving straight from an inertial reference frame. So we want to figure out the terms, basically how can we write the inertial reference frame of the velocity in terms of the non-inertial reference frame. So to start, we define the position vector, which is x in the x direction plus y in the y direction plus z in the z direction. And so it's a vector of basically x, y, z. It tells you where you are positioned at a single time, or where the air particle is positioned at a single time. And so we take the time derivative of our position vector in inertial reference frame, and we will then use the product rule for each term. The product rule, if you remember, is d of f times g dt is equal to f dg dt plus g df dt. And so each of these terms will have two terms, so we'll have a total of 6 terms. So we will get I dx dt plus j dy dt plus k dz dt plus x di dt plus y dj dt plus z dk dt. And we can write this term as the total derivative of r in the non-inertial, in the rotating reference frame. And so that term goes here, and this term goes here. And we can show through a bit of geometry and trigonometry that these terms di dt is equal to omega vector crossed with the I unit vector, x unit vector I, and that dj dt is equal to omega vector crossed with j, and dk dt is omega vector crossed with k. And we have that omega vector is equal to omega, which is the rotational radians per second, so that how much the angle changes per second of the Earth's rotating on its axis. And it has a direction cosine latitude, so this phi symbol is latitude in the y direction, so j, plus sine of latitude in the k direction. And we will discuss in another video, first of all, why we define omega vector like this, and how these terms were solved for, what kind of method for getting these. And we'll also find in another video that we can also expand these terms into partial derivatives and expand these terms even more to a point that we will come out with an even more expanded form of the two forces, the two imaginary forces that is going to get derived in this video. And so we can then use this fact, and we'll get that dr dt in the inertial reference frame is equal to dr dt plus omega vector crossed with xi plus yi plus z plus yj plus zk, and that's just as we defined before to be the position vector. So now we have that is equal to dr dt vector dr vector dx, dr vector dt plus omega vector cross r vector. And since this is actually also true for any vector we put in, we can also apply it to this vector ui plus vj plus wk. Okay, and so we can basically take this form of our equation here and just plug in ua for r, where u is the inertial velocity, and we will get dua dt in the inertial frame is equal to dua dt plus omega vector cross ua vector. And we also should notice that the derivative of r in time is actually just r velocity, because we have a location, and the change in that location over time for x is just equal to u, and dy dt, that's equal to v, and dz dt is equal to w. So knowing that u is equal to dr dt, we can now plug into this equation. We'll get ua, because we put u here, and then ua is just equal to ua, and on the right hand side we plug in this is u, so we have u, and then we keep this part the same. So we have this omega vector cross r vector. So now we can plug this into here. So first, looking at the total derivative term, that's right here. We have the du dt plus d this dt. And then we have omega cross, then ua vector, which, as we defined here again, is just right here. And I apologize, that is actually typo, that is also u. And we can also, for this term, we can take omega out, so it's here, and we have the dr dt, and this is u, so this is omega vector cross u vector. So now we have that this is equal to this plus this plus this. And we can see, for this term here, this is equal to omega vector cross u vector plus omega vector cross omega vector cross r vector. So this cross this plus this cross this. And this term plus this term is 2 omega cross u, and then we're left with omega cross, or this term, omega cross r. So this term here is called the Coriolis force. which is that curving away of the trajectory that we saw. And this term is the centripetal force, I believe. I believe it is not centrifugal, I believe it is centripetal force. And let me just double check that so I don't make a big mistake. So that is the centrifugal force. And the centrifugal force, let me see what the definition is. It's when you're driving in a circle, there's this outward motion that doesn't actually exist when you see it in the inertial frame, but if you're following the path of the circle, you do feel a force taking you outwards. And these are, of course, two imaginary forces that don't actually exist. They're just based on the viewer's perspective. And if you remember, again, we wrote this at the beginning of the video. We know that this is equal to this. So we have this is equal to this, and this is equal to this. So we can set these two parts equal to each other. So we have, let me correct something here. We have these two are equal to each other now. And we can subtract this term on this side and this term on this side, and we will get du dt not in the rotating form. This term is equal to negative 2 omega cross u minus the pressure gradient force plus this k dot gm. And we can also include this centrifugal force inside of this term, and we will call the entire term k dot g. So this force only occurs in the z line of the atmospheric equation, and g is a combination of the force of gravity and centrifugal force. And we have the friction, which should actually look like this. My apologies. Okay. Let's see, yeah, it was like that in the beginning. So it's the Laplacian, not the gradient. So as we see here, G is defined as gm, and we can say it is minus k dot this term, and where gm is again defined as negative gm over r squared, which is equal to negative 9.81. And as you'll notice, why did we put a k here is because when we do g with a k, we get k dot gm, which is what we originally had, and this k times k is actually equal to 1, so we'll just be left with this part of it. And so finally we have our equations. Du dt is equal to, which is really a three-line equation with x, y, and z components of velocity, or otherwise known as u, v, w, is equal to the Coriolis force, negative 2 omega cross u minus alpha gradient p plus k dot g plus this term here, mu Laplacian squared of u. And then again, we define g is equal to gm minus omega cross r, and this gm is defined as negative gm over r squared, which is about, actually we showed in the last video, negative 9.82, just assuming the average mass of the Earth and average radius of the Earth, without accounting for topography like mountains or the vertical variation of gravity. And so in the next video, I will describe why we have that di dt is equal to omega cross I, and the same for similarly for djdt and dkdt. And then in the next video that I make for this series, I will discuss a more fuller expansion of these terms, which actually give us even more terms to come out of this term here. So we will still have this term, and we'll have some more terms that will show up, and they're just an expanded version of the Coriolis force, including the effects of the curvature of the Earth. And for one final thing in this video, I will show how this force looks like. These we've seen before, but this one we have not as well, but that one I may do as well if I have time. But first we'll do this one. So we have 2 omega cross u, where omega is equal to, I believe, cosine phi j plus sine phi k. Let me double check. Cosine, correct. And u is equal to ui plus vj plus wk. Okay, so using the definition of curl, we have this one's actually a little bit more. This term has omega, which is just a scalar, or not scalar, a constant radians per second. So we have that this is equal to 2 omega times the, my mind is blanking, the there's a term for this this type of thing, but I'll just go through it. For the definition of curl, write the I, J, K, and then you put the left-hand term. You put the I component of the left-hand term, J component, and K component, and that will be 0, because there's no component for I. Then we have cosine phi, that's the J component, and then the K component will be sine phi. And then for U, we'll just have U, phi, and W, phi, W. And for this term, if you haven't seen how to do this, I was just looking it up, and just for the sake of the video, I'll get the name of that term. that is the determinant of this notation here. That is the determinant. So you can look that up online. Okay, great. So we have 2 omega. We will get a term that looks like this. The I times this minus this times this. So that will be W cosine phi minus V sine phi times I. And we can write this like this. Minus J times something. And that something will be 0 times W minus U times sine phi. So it will be minus U sine phi plus K. And that will be, we cross out these. So like for the first part, we cross out these, we look here, take the inner determinant. Here it's minus this one, take this determinant. Then again, and finally we do this. It is U times V minus U times cosine phi. So we get minus U cosine phi. And so this is equal to 2 omega, and let's close this. Cosine phi minus V sine phi I plus U sine phi J minus U cosine phi K. So this will be the Coriolis force written out. And then I will also show this term, the U cross R. So, omega cross omega cross R. Knowing that omega is equal to omega times cos phi J plus sine phi K, and R is equal to xi plus yj plus zk. So for the first term we have this equal to the determinant of I, j, k times 0 cos phi sine phi, and then x, y, z. So this is equal to, let me think, cos phi z minus sine phi. Actually, when you write it in a way, that'll be easier to see. So z cos phi minus y sine phi times I. And we have a minus times j. Let me see. 0 times z minus. So it'll be a minus is a plus. It will be x sine phi plus something times k. So be a minus x cosine phi. So that's that term. Now we need to do the final step, which is, let's just call this A. So we'll have omega cross A is equal to I j. Okay. So that is 0 cosine phi sine phi. Then we put these three terms in here. So we'll get z cos phi minus y sine phi. You have x sine phi minus x cos phi. Let me just double check that. Okay. 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 K will be right. So we have three terms. The first term, second term, and third term in line like this. This will be equal to something a bit complicated, so let me add another page. Something times I, that something being minus x cos phi, or cos squared phi, plus x sine squared phi. And what's this? Note, I noticed something about this is you can take, let me see. Okay. Oh, you cannot. Okay. Well, that was close, but I was hoping we can get rid of the sine squared and cosine squared, but that will not be possible. So next we have minus j here. So that's 0. So we have z sine phi cos phi. Yeah, let me think. It'll be plus because the minus cancels out. So z cos z minus y sine squared phi plus k. So we have this and this. You have z cosine phi, cosine squared phi minus y sine phi cos phi. So that's a very complicated term. So usually when we're doing some sort of calculation like with a computer, we do not write the whole thing out. We simply, well, actually we might write the whole thing out. I think what we simply do is we use this original form, such as this form. First we use the computer to calculate this one, then we just combine that into some sort of matrix, and then we take the curl of that matrix. So we have some sort of notation that generally works for matrices, and we don't write out all these terms. We can simply plug in these as functions. So, a more easier, simple way that this is done is simply, writing that we have, A is equal to maybe A1I plus A2J plus maybe like this, X, Y, Z, K, and we have B in the computer as BXI plus BYJ plus BZK, and then we set up that A cross B is equal to, this kind of notation. You have ax, ay, az, which I'll set up in the computer, which is then equal to aybz minus azby times I minus j. So we have axbz minus azbx and plus the k term, which is axby minus aybx. And now we have one for each line, and we don't need to mess around with any sort of complicated things, zeros and things like this. This calculation will all just come out by the computer. So this is just nice to see what the full equation actually looks like. But again, it's simply just easy to use the vector form of the equation. So that will be all for this video, and I hope you learned something, and please, if you're interested, stay tuned for the next video.